Good afternoon. Today I will be discussing the dynamics of mid-latitude gyres and their roles in ocean currents. Uh, Let us first discuss the formation of mid-latitude gyres. There are four main reasons. They are the global wind forcing, the Creole's effect, the boundary effect of continents, uh, and the Ekman transport and pressure gradient force respectively. The formation of mid-latitude gyres begins with the global wind systems, particularly the trade winds and the westerlies. The trade winds occur mostly near the equator, which blow from east to west near the equator, pushing surface water westward. And westerlies occur mainly in the mid-latitudes, which blow from west to east in mid-latitudes, pushing surface water eastward. These wind patterns initiate the rotation of ocean waters in mid-latitudes. For the second reason, the Coriolis effect caused by Earth's rotation deflects the motion of water and air. In the northern hemisphere, water is deflected to the right of its motion. In the southern hemisphere, water is deflected to the left of its motion. This deflection creates clockwise gyres in the northern hemisphere and counterclockwise gyres in the southern hemisphere. Thirdly, continents act as barriers that redirect ocean currents. When currents encounter continental barrier boundaries, they change direction and close the gyre loop. Western boundaries, like the east coast of the Americas, typically from strong warm currents, while eastern boundaries, like the west coast of Africa, will create weaker cold currents. But the interesting thing is that gyres are not symmetrical, and why is that? And why is that? Then I have to introduce the concept of conservation of potential vorticity. Now I'm going to take you through the conservation formula. For the potential vorticity, it is equal to the relative vorticity zeta plus the planetary vorticity f, and divided by the thickness of the water column h. The total vorticity of a fluid element is the sum of the zeta and f, where zeta is equal to this one, and f is equal to double ohm sine phi, which phi is the latitude and ohm is the Earth's rotational speed. Now consider a water column of thickness h moving in the ocean, assuming no mass is added or removed. The volume of the water is conserved, so HA is constant, where A is the cross-sectional area of the water column. So we can get the differential of the potential vorticity to 0. So the potential vorticity is constant. So as a result, at high latitudes, as the water column moves to high latitudes, F increases due to the Coriolis effect to conserve potential vorticity, as the zeta must decrease, and reducing relative rotation, or H must shrink. Conversely, at low latitudes, as a water column moves toward the equator, F decreases to maintain conservation, so zeta must decrease, or H must grow. So, in reality, for the western boundary currents, in systems like the Gulf Stream, vorticity conservation explains why currents intensify along the western boundary of the ocean basins as water moves polarward along the western edge. F increase, so and the current becomes stronger. And the asymmetry of gyres arises because vorticity is conserved and leading to intensified flow on the western side of the ocean basin and weaker flow on the eastern side. As a result, the gyre formed. The fourth reason, aircraft transport and pressure gradient force. Wind-driven surface water movement is deflected due to the aircraft transport, causing water to accumulate at the center of the gyre. This accumulation creates a high pressure region leading to geostrophic flow, which is a balance between the pressure gradient force and the Coriolis effect, which stabilize the gyre. In conclusion, mid-latitude gyres are not just fascinating phenomenon but also vital for Earth's climate system. Thank you very much.